So please allow me to make a brief self-introduction. And my name is Zhu Qian, and I specialize in researching writing technicals in the cloud. And my partner Cao Zong used to be a bug hunter in JavaScript engine and a WebAssembly engine, and has present his work on Black Hat Asia and USA. Now, I will start by introducing microservices, an important component of cloud platform. As we all know, cloud computing is a technology that allows us to store, manage, and process data over the internet instead of local servers. So on the other hand, microservices represent an arch approach that breaks. What that happened? Oh, okay. On the other hand, microservices represent an arch approach that breaks applications down into smaller and independent parts. So each service is designed around a specific capability and communicates through metadata API. Together, cloud computing platform and microservice create a synergistic relationship that the platform providing a powerful and scalable environment for deploying these microservices. Next, let's turn our attention to JavaScript. JavaScript is one of the most widely used programming languages in the world, and it holds an important position in web development, in mobile, desktop applications, and so on. I have to say, I was amazed by the awesome syntax of ECMAScript. So in a lot of microservices, you might have noticed that script syntax is often similar to the ECMAScript standard. When we look deeper into how this works, it turns out that what we are actually doing is running the user input as JavaScript code, and then we throw it to V8 engine. So we call this case as JavaScript as input. At times, these secrets are even bunked up in coders like JSON, base, and storage in pack scripts, circle scripts, and the like. So let's take a few examples to reveal it. The first type of example is JavaScript in Cloud Functions. And we also call these serialized functions in cloud, like some old friend AWS Lambda, Google Cloud Functions, other functions, and so on. These services are very popular, and their backend server has both connection with JavaScript engine, and we can find them. Secondly, famous as headless browser services, like web crawlers, taking screenshots, parsing web pages, and other similar tasks. Recently, we have noticed that some large language model agents are actually leveraging JavaScript engines to power this function too. Thirdly, we call the database applications. It's fascinating to say JavaScript not just as a front-end language in web pages, but also embedded in databases. Some document-based databases like CoachDB, PostgreSQL have their own built-in JavaScript engines, which is quite handy for more complex query. And there is last one example. We call the remote browser isolation. I'd like to call this Chrome as a service, and one popular toy called the browser box, and you can find it in GitHub repo. So when we consider these microservices as input, it flows into a pipeline. We typically encounter two types of scenarios. One is browser-based, and the other one. One characteristic of these scenarios is that they pass user input to JavaScript engine for execution, And after the exaggeration, we get the result from cloud platform or tenant's bucket. Okay, hacker attacks happens during the initialization of containers and the JavaScript engine. So I will detail the potential attack surfaces for that progress. First, it's crucial that whether the JavaScript engine parameter sandbox is disabled or enabled. This is important because it directly impacts the possibility of exploit. However, we must consider some situations where the no sandbox option is set by default. For instance, when WebDriver binary runs as root user instead of a Docker container or whatever Unix system, disabling the sandbox becomes necessary. So look at these two pictures. We spotted the evidence of this practice in V8 engine's code, and we also found a lot of discussion about this issue. Why I should turn this sandbox down. So the second attack surface is that many proof of concepts or exploits appear to be effective only when specific flags are able. Let's take a V8 engine as an example. Many flags still in a developing state, which means some experimental features are not stable and can be vulnerable to remote code exaggeration, such as feedback normalization and several flags in WebAssembly. Even more, the compiler, if we use these flags to bring ourselves in a dangerous model, we will say a lot of new features and we can exploit. So if I report to Google, I say, hey, I was able to attack your product by adding a flag generated not recommend, and if that would be a security issue, and could I receive your bug bounty? The answer is clearly no, because Google's flag design are not meant to allow you to override these flags, and no developer should configure them in this way. So, but it raises another interesting question. In microservice situation, do we actually have the capability to enable these flags? The answer is interesting too, since each tenant is responsible for managing their own resources. Sometimes they are also permitted to adjust certain elastic flags. All right. These flags help limit memory, thread overhead, and so on. Crucially, citing these flags can be a prerequisite for the exploit. That means on the cloud platform, we might just have the capability to manipulate these settings or flags in even more vulnerable scenarios. We can change these settings or flags via injection attack or parameter injection. Well, and there's still an important surface about ND attacks. We noticed that the amount of software integrates the V8 engine's code through static or dynamic linking. This makes patching any vulnerability for V8 engine quite challenging, as it often requires the software to be recompiled, and we might be lazy to do that. Well, for the three attack surfaces just mentioned, let's look at the situation we faced. Logically, the three issues mentioned in the slide should be related, and it's intuitive to check just injection first, and then the sandbox enabled, and last, the check version. However, in the real-world environment, sandbox detection is actually very, very, very difficult. And in most cases, the sandbox can only be checked by confirming its version, and know its version then using the shellcode to check it. So the order of 1 and 2 and 3 should look like that. That means the detection of JavaScript injection is always case by case, which has nothing to do but with the engine itself. And the version detection actually becomes the core of this process. It's the part that takes up most of our time to check version. All right. The following time, my partner Cao Zong will share his thinking about using large language model agent to work this out.
Hello, everyone. I'm Cao Zong. Okay. When we just facing JavaScript as input services, before any exploit, you just need to know exactly what versions you are actually dealing with, and most of the time, different versions have different exploit techniques, right? And you need to concern about different offset. You need to debug on your local build. So it's very important to point out that when a service uses browsers as a web driver like Puppeteers, you can easily fake the version by changing the user agent. So in these cases, we cannot rely on the user agent for judgment, right? We need to monitor it dynamically. Let's first see how people think about this issue. If we do need to check the version dynamically, how do we do that? First, we have got lots of sources. Human experts dive into the relevant document, commit, and key issues related to the target. They try to identify features that help determine the versions, right? And for example, let's look at the Chrome project. It has a platform status page that lists updates related to the Chrome features. Those kind of features include the updates related to the JavaScript features, of course, and there are also some features that are not suitable for testing in a JavaScript environment, such as the update to the DOM features. This is because the JavaScript engines is currently mainly served as a part of the browser engines and on the client side. So major version updates still need to be extracted from the feature updates page provided just by the mainly browser vendors. So if we consider the situations that include more detailed contention include just related to the DOM, the Chromium Checker project, mainly maintains updates on the some Chromium versions features. But however, in the JavaScript environment, those browser version updates can only be marked from a broad perspective, right? JavaScript-related features update are not that kind of frequent. So if we just want to study the differences between versions in more detailed perspective, so we need to dive deeper into specific commits or issues. Okay, similarly, the Firefox Diva platform provides the same pages and detailed record to update between versions, and which also include both JavaScript-related update and non-JavaScript-related update. Okay, then you need to understand the feature changes from those documents. Sometimes this involves linking additional links to fully grasp the details. This is a process we call it context filling in the human's mind. This is really useful as most of the time it must even include the test cases directly. And here we need to emphasize that we are particularly interested in the test cases that can highlight version differences, especially test cases that can directly affect the output before and after a patch. So the next step of the human expert is we need to test on the specific platform, right? The method can be varied. Some services allow version determination through console output, and other maybe require checking HTTP response code. In some platform need maybe require you to do some login information check. the method are vary in these cases. So let's think about what AI can do in the workflow. We know here are two tasks that are particularly human labor demanding. The first one is understanding the content of the document. And the other is writing test cases based on that understanding, the same context, right? Those tasks are very time-consuming for humans or hackers or pen testers. Sorry. Therefore, in the era of AI, we want to use LLM to solve some of those problems. Of course, we agree that the AI cannot solve general security issues, but by designing appropriate task for AI, we can just accelerate the security research itself. So, okay, on the left side is two tasks involve information input and collection. In fact, this isn't much different from traditional automatic development tools, but so that would be no enhancement if we use AI. So yeah, that's not an area of yeah. Back to the task one. The main task of understanding the code here is to comprehend the contents related to the document and relevant test cases and patch files, commit information, etc. The overall design idea of the prompt is to determine whether you can judge if this update can be triggered in a poor JavaScript environment without relying on any kind of DOM element. And additionally, if you just need more context, where you can obtain the information obtained from. Okay, so our agent framework primarily includes several key actions. Mainly consists of two types, the chat actions and tooth calling actions, which are very similar to the traditional state machine model. So this is a loop of our context filling, and once you just find the interest link, you can just tell the LLM to do the function calling for you and fix the same context and do the parameter again. That is just an iteration. Okay, test case generation and the fixing both, and the fixing work both aim to produce samples for the testing. Generation involves creating samples based on the current test of the state machine, and while fixing is more like code migration. The challenge here is to adapt the test files with certain built-in function calls. Many samples it just directly extracted from the open source project that contain many built-in functions like assertions and JIT-related functions. So makes them more genetic is a problem, and it's what AI can just help us to do. This involves converting less genetic samples into a more universal state. Okay, due to the limit of the time, we cannot introduce a complete agent design, including differential check-ins, differential version check-ins, and the lifetime filling. We just focus on the core parts related to the LLM to convey our approach to the test case generation. Using the agent, we extract a basic version identification tools by table from update documents and find granted version identification list from the commits. Each list corresponding to the transformed test case with different behaviors before and after the specific version and lifetime of samples. We plan to release the JavaScript engine checker maybe later this year, but the tools is now currently undergoing final stability improvement. Okay, so next we will review two cases. The most common vulnerability scenario is headless browser applications. In headless browser applications, usually it's just a need to headless browser request with the user-controlled URL. And once the web driver visits the malicious URL controlled by the attacker. It will just attempt to parse and execute a JavaScript statement under the script tag. So finally, the JS engine executes the shellcode presented by the attacker and failed the file. This is the three pictures and and the three pictures in slide can just some fragments of the code that we found in the real world cases. Given URL for web screenshots in many web pages, we will just provide such functions in the shady in the corner, such as web monitoring services, and even in vulnerability scanning services provided by some online scanners. Perhaps do you remember that Bob Suite used to have the same problem with that? It has the same functionality like JavaScript scanners. The second attack case is the hacking database, and based on the past pen testing experience, any procedure language could have an engine parsing problem, execution problem, and we actually found a vulnerability in the PG-SQL plugin. First, we create a PG-SQL database on the cloud computing platform. Many vendors have just use a PG platform as just as a part of the cloud database services. And next, we use the create extensions method to activate the JavaScript procedure language plugin. And we just found that the plugin uses V8 engine, the static library, and power its built-in functions, parsing, and kind of thing. Using the version identification technique described earlier, we just found that the version of V8 engine is too undated and just could be vulnerable to end-day attacks. Okay, this picture just shows how we detect the versions of the V8 engine during the exploit. As you can see, the JSON stringify functions as a parsing difference between the version 9.7 and the earlier versions identified by our agent. This is a part of the node of the table. In using these differences, we successfully distinguish the boundaries of the real-world versions to 9.7. So in the end, we utilize a well-preserved end-day vulnerabilities to escape from DB host privilege to the system host privilege and receive a nice bounties from many cloud computing vendors. Okay. So finally, we propose three mitigations. We all know that updating software components can be a very complex business. So is it possible to work on the flags of the JavaScript engine, such as a convention, no sandbox argument, or jitless arguments? Since the WebAssembly is disabled in the jitless model, so you can just, this is a way to invalidate most of the exploit technicals. And what's more, we know that many vendors choose to use debug versions to adding many assertions or the dechecks to just do the same thing to invalidate the exploit. And in addition, we are also exploring new ways to detect such vulnerabilities, and we just looking forward to share them with you in the future. Okay, certainly there is one more point that need our spatial attention: the ability to extend to other applications that include JavaScript. In fact, you may just notice that we initially focused on our analysis in the cloud environment, right? Since this talk is to summarize various scenarios in cloud environment where JavaScript environments are used, but however, there are many other scenarios such as Electron, web views, and VPN, pack, etc., where JavaScript is also widely used. And enumerating those cases is not a great idea, right? You would always miss something. So we aim to understand the impact of the JavaScript environment on the entire software ecosystem. We intend to analyze the conversion and the vulnerability in the use of the JavaScript engines in the software dependency graph to identify security risks. This goes beyond the scope of the SCA, which is a software component analysis, and it really requires understanding of evolutionary of the software itself, software ecosystem of the JavaScript engines, right? This is very similar to kind of researchers in the biology, pathogenic genes, aiming to just understand which species pathogenic genes might affect. In this analogy, conservation corresponding to the software dependencies, while vulnerability corresponds to different configurations or measures that would just affect the exploit. If we make further progress in this area, we will just share our findings with you. Okay. So, the above is all the contents we shared today, and this is a takeaway. The first, we introduce GAI and definitions and its scenarios of the applications in the cloud computing, and introduce the JavaScript as input attack surfaces and corresponding attack vendors. And next, we introduce how to use LLM engine to collect features of the JavaScript engines and do the identification works on the black box, remote JavaScript input point. And finally, we apply some JavaScript features to detect and execute in-day attacks on the database services and the headless process. Okay, thank you. That's all the contents of our talk. So if you have any other kind of questions, please feel free to just DM us on the Twitter and now it's X. Sorry. Okay. So thank you very much.